This is the video answer guide for the study guide for Unit 3, ELR 3.3. This one's all about mass and gravity and distance. For this one, I want you to be thinking about the interactive that you did on the computer where you were trying to figure out what causes gravity or what are the variables in gravity. And I'm going to pull that up in just a second, but it all came from Newton. Newton said that there were two things that affect gravity, and they are going to be distance and mass. Basically, the way that it works is the more of either, the more mass there is, the more gravity you will be experiencing. So if you are standing on a large planet, you're going to feel more gravity than if you are standing on a very small planet. But also your mass makes a difference. So the more mass you have standing on a large planet, you are going to feel a lot of gravity compared to a smaller person standing on a large planet. So the mass of both objects makes a difference. Also distance apart. The reason why you feel gravity really, really close to the Earth and as compared to when you start leaving the Earth is because the distance plays a role in that. So to go to the interactive, it looked like this. In this interactive, what you were able to do was adjust the mass of these two objects, and this little arrow right here in the middle is what's telling us how the force is responding. So in other words, how much gravity is pulling. So I want you to imagine that this little red dot right here is a planet or an object, it could be anything, floating out in space, and the center where this arrow is also another object. These two things are supposed to be the radius, so like if you were to imagine that these objects were gas planets, the radius of the planets would be being adjusted to, but we're not going to deal with that. We are just interested in what happens to this arrow, or the amount of force from gravity that these two objects experience. So, first thing is if you drag these things closer together, the force arrow is getting greater and greater. So the distance plays a big role. But let's think about like how it plays a role. If I am way out far away, this on the interactive is far away, and if I start dragging it in, try to keep it at a consistent rate, the arrow doesn't change a whole lot at first, but as I start getting closer and closer, the arrow kind of takes off. So as you get closer, bring two masses together, the gravity starts ramping up, and it's exponential, not linear. The other thing is the mass. So if I start adjusting the mass of either of these things, when I adjust the mass of the first object, obviously the more mass, the more gravity there is. But if I adjust the mass of the second object too, that also affects the gravity. So you are actually, when you're standing on Earth, Earth feels like it's only pulling on you, but you're also pulling on the Earth with a little bit of gravity too. And the force that you're pulling on the Earth is the exact same as the Earth is pulling on you, because equal and opposite forces, Newton's third law. So back to the study guide. Number 2, suppose two bowling balls were floating in space, and one of them had a mass of 10 and the other has a mass of 5, and it's asking what's going to happen. The trick here, or I guess the maybe trick, is that a lot of people think, well, because there's a big one, I bet the big one is just going to pull on the little one, and the big one's going to not even feel a thing. That's not how it works, but you're tempted to think that because it feels like the Earth is the only thing pulling on you and that you couldn't possibly be pulling on the Earth. But according to Newton's laws, anything with mass has a pull. It pulls on something. So as we look through the choices, A says they will not do anything since they are both objects at rest. Well, because they both have mass and they are some distance from each other, they're going to pull on each other with some amount of gravity, so A is not it. Letter B says the bigger one is going to pull on the smaller one, and the smaller one will move toward the bigger one, but the big one won't move. That's not true either. They're both going to be pulling on each other, so there's going to be a force on both of them, and as long as they're just out floating in space, they're both going to feel a tug, and they're both going to move. So B is not it either. C says the smaller one is going to pull on the bigger one, and the bigger one will move towards the smaller one, but the smaller one will not move. That one's not it either for the same reason as B. D is correct. They will each pull on each other with the same amount of force. So if you have the small one and the big one's going to pull on the small one with a little bit of force, but at the same time the small one's going to pull on the big one with the same amount of force. They're going to pull on each other with the exact same amounts of force. Number 3. Sketch a graph for the amount of force from gravity in object fields as it moves away from a planet. So I want you to imagine that you've got some planet, and maybe there's a little spaceship on the planet, and it's going to take off and head off that way. And as it travels away from the planet, we're going to talk about, or make a graph for, how much velocity it's feeling as it moves away. So to make this graph, it says in the instruction that on the x-axis we're going to say time, And on the y-axis, we're going to say force. We're not actually putting any numbers on this thing. We're just going to draw a sketch. So let's consider two extremes on this time thing. As a thing sits on the surface of a planet, their distances are extremely close to each other. And so the closer the distance, the more force. So at the beginning of the trip, there's quite a bit of force. We're going to put a point up there. However, as the trip gets to its endpoints and the rocket's way, way far away from the planet, there's going to be very, very little force. Not zero, though. You can never get fully away from gravity. I mean, it can get pretty ridiculously small, but it's never zero. And if you remember from the interactive, it's not linear. So these two things are not going to have a line like that dotted line I've just added. Instead, it's going to be a bit of a curve. So in the beginning of the trip, as you move away from the planet, the force from gravity is going to drop off quickly and then slowly start to level out as you get further and further away.